Okay. Okay, let's begin. In the last class, we kind of saw that for realizing high resolution ADCs, delta sigma is the way to go, right? But we should also understand what the limitations are, right? So, I mean, in delta sigma, the one of the main limitations is, see, here we kind of rely on noise shaping, right? But noise shaping alone is not enough, right? What do we do along with noise shaping? We have to do oversampling, right? Because signal bandwidth has to be small. So since we are oversampling, if let us say your signal bandwidth is some b and your oversampling ratio is m, what is my sampling rate? What is sampling rate? This is the signal bandwidth b, this is the oversampling ratio. What is the sampling rate? No. I mean, at Nyquist rate, what will you sample? 2b. So now what is the sampling rate? This is a Nyquist sampling rate, right? So this is my sample rate. So basically, if I keep increasing my signal bandwidth, the sampling rate I need will also keep increasing crazily, right? Because you need large oversampling ratios. That sort of limits it to relatively low frequencies. So till around hundreds of kilohertz to few tens of megahertz, we sort of do it. And at high frequencies, beyond that, it becomes difficult to do. And as it turns out in practice, luckily, the applications are such that at really high speeds, you don't need high resolution, right? And you need really high resolution at low speeds. Okay? So if you have to show it like this, let us say here I show the speed. So here let's say I show the speed from, let us say, low to mid. And here I show high speed. Similarly in the resolution range, so here let us say low and high. It turns out we need things, at low speeds we usually need these guys, and at high speeds we need these guys, right? So here is where delta sigma nicely comes and fits in. Now at really high speeds, where like the speeds are hundreds of gigasamples per second, the resolutions are really low, like 5 bits or 6 bits. So there we do this time interleaving with SAR, because that's the only way in which you can get ultra high speeds. Now slightly lower, let's say a few gigasamples per second or few tens of gigasamples per second, is you have to use pipeline. That's the only way in which you can get around 10 to 12 bits of resolution at high speeds. And luckily, till now, this is something that is not been required. Ultra high speeds and ultra high resolution. Cool. So yeah, now I wanted to discuss another aspect with delta sigma. So if you think about it, our delta sigma as of now looks like this, right? So we have the loop filter here. It's a discrete time loop filter. And let's say here is where the quantization noise is added, and we close the loop. And remember that we choose the loop filter to get a particular noise transfer function. So which means if this is 0, from this q of n to the output I want some particular noise transfer function, right? So from a given NTF, NTF is how you find the loop filter, right? Cool. And you know that this is realized using switch capacitor circuits. So explicitly I will just show that the signal is sampled prior and then we are filtering, right? And the input, any switch capacitor circuit, the input stage sort of looks like this, right? You have something that samples the input and then you have rest of this. So I'll just say this is my rest of the ADC. Okay. And you know this switch is going to have some on resistance in practice, right? And also remember that this is usually driven by a buffer here, right? So again we have seen this multiple times. So let us say the capacitor is initially uncharged, the switch is closed at this time instant, what will happen to the current drawn from here?
It will be like
At the time capacitor is initially uncharged, the switch is closed, it has a resistance of R on, it will take in a current of V in by R on, initially it is 0 and then it spikes up to V in by R on and then it sort of decays to 0. Now for the same sampling capacitor, if I increase the sampling speed, what can you say about R on? R on will reduce because you have smaller and smaller time for settling. For the same capacitance, RC time constant will reduce, so R will reduce. So this current will keep increasing crazily, right? And remember, this current has to be provided by this guy buffer here, right? So in practice, it is not just enough to design the ADC, right? See, you would have designed this ADC itself to have 100 dB of SNDR, right? But you should also make sure the buffer is not limiting the overall resolution finally, right? It's not enough just for this to have SNDR of 100 dB. This should have at least 100 dB or better SNDR, right? So designing these buffers which can provide these spiky currents and maintaining that high linearity it's actually very challenging. So this buffer power and linearity is actually critical, and we kind of saw this in SAR also, but it is true for any ADC. And also more fundamentally, if let us say my input has a frequency at, I'll just say k times fs plus delta f, if I sample it at a frequency fs, what will happen after sampling? It will alias back to delta f. This is aliasing. This is something fundamental that is not preventable, right? But what can you do to reduce the effect of aliasing? You have seen it, right? See, the point is, before sampling, if this signal here has a content at fs plus delta f, you are gone. So what can you do to reduce the effect? Before sampling, what do we do usually? We have to filter it off, right? The point is, only if we have content at this point, only if you have a frequency content at this frequency, you have issues. So you put a low pass filter upfront or an appropriate filter upfront to filter those frequencies, and this was what called the anti-alias filter. So before sampling, you also have to have this guy. So we already seen in the beginning, first class itself, right? So you have to make sure that this is noise or anything, right? See, anything present at this frequency when sampled at fs will alias. So you have to make sure that these guys are not these guys are filtered out.
Means required is delta f, that's the reason here.
It can be anything. In general.
Okay.
Right? Before sampling, you have to filter high frequency stuff. What is that frequency component? It depends on the application.
Okay.
So it is not enough to just have the buffer. You also need to design this filter, and that should also have the same linearity, right? So this anti-alias filter also becomes tricky to design. So this prompted people to see if something can be done, and what that something is this. So right now what we are doing is this, right? So in delta sigma at least we sample it, and then we have the filtering. So let me write it like this. So okay, we have some x of t which is first sampled, and then let us say we have a discrete time filter h of z, and let us say that gives y of n. So instead people thought, hey, why can't I do this? Let's say filter it in the continuous time domain itself using a continuous time filter, and then I sample it, and if I somehow choose this filter such that for the same input I get the same samples here, I am saved, right? This at least logically makes sense. I'm sure, I don't know if in your signals and systems you have seen this discrete time to continuous time mapping. You not seen? Okay, fine. But at least logically makes sense, right? You should be able to do this, right? And the reason for doing this will be apparent soon. But let's say you do this. So now the discrete time loop filter here will now become continuous time loop filter. So let me actually put it here. So instead of this, I will now have it like this, where first I don't sample, I do the filtering in the continuous time itself, and then I sample. And again, the idea is same. You have a particular noise transfer function. From the noise transfer function, you find the discrete time loop filter. I will write it as NTF of Z. From NTF of Z, you know how to find the discrete time loop filter L of Z. And once you know the discrete time loop filter L of Z, again from MATLAB, you can instantaneously find what should be the continuous time loop filter is. Right? And the idea is you have to make sure that you get the same NTF, that is the impulse response from this point to this point is what you want. That's all. And this usually this implementation with switch capacitor circuits here is called discrete time delta sigma modulator, and this is called continuous time delta sigma modulator. Okay. So again, before getting into details of how this is beneficial, let me just mention this. In a discrete time case, the loop filter, how did the loop filter look like?
In first order.
Let's say the second order, let us say.
Okay, it was 1 upon NTF minus 1, right?
Yeah, but what, that's okay, that's but
K1 into...
it's a cascade of integrators,
Yeah.
right? So it was of the form K1 times, let's say Z inverse by 1 minus Z inverse,
plus
K2 times cascade of 2 integrators, and so on, blah blah blah. Now in discrete time, the loop filter is a cascade of discrete time integrators. In continuous time, what do you think it will be?
It will be cascade of continuous.
Cascade of continuous time integrators. Again, I am hand wavingly explaining this. I think that's okay. So it will be some K1 hat of S, K1 hat by S plus K2 hat by S square, and so on. And it turns out these guys need not be equal. It depends on what the mapping from discrete time to continuous time filter is, right? And this will not be equal, but the form will be same. Okay, cool. So now let's actually see if this is even better, right? And for this, let's take a simple first order case. First order, you just have one continuous time integrator. That's all, right? Yeah, I'll just explain. That's what. If you look at the implementation, becomes clear. So the continuous time integrator, it's going to look like this. We just have an RC using an op amp. Integrator, everyone is fine. So after the loop filter, I'll have the sampler. That's where I sample, and then I, let us say, have a single bit quantizer, and then this has to be fed back. So that's also in continuous time like this. So remember, here the quantizer will give 0 or 1. If it's 0, you connect this guy to 0 volt. For 1, you connect it to VRF volts. That's all.
What did you do this upper?
Huh?
The upper...
You have to subtract, right? I mean, the feedback is this, isn't it? Let's say without the quantizer, it is this.
Yeah.
This is the input and this is the feedback path. Fine? So let us say this is R, this is R, this is C. So here, if at all I have any input buffer here, what will be the current that we are drawing from this buffer? V in by R, this is virtual ground 0 roughly. So the current will be constant and it will be V in by R. So if I sketch this versus time, it's going to be a constant current V in by R. Now in a discrete time case, when we had a switch capacitor input, the buffer current, how did it look like? It was a huge spiky current and it shot up to V in by R on. So do you think V in by R on will be larger or this guy will be larger?
This will be rather.
Why?
R is very small, right?
Yeah, R on is going to be, I mean, at least loosely speaking, this is the on resistance. Ideally you want it to be close to 0. So this will be huge compared to this, right? And I mean, generally also, how do you think we'll be choosing the value of this resistor here? What do you think might decide the value of the resistor?
The integration RC constant or maybe.
I mean, the RC time constant says value of R and C. We have choice to choose both, right? Okay, or at least in a discrete time case, the input was sampled on a capacitor. How did you choose the capacitance value here?
From noise.
From noise. So here the noise is sampled, so you are looking at sampled noise, which is kT by C. Here the noise is not sampled, it is continuous time. So what is the path spectral density for a resistor? 4 kTr. Okay. So if I plot the path spectral density of a resistor,
SPN, right? SPN is 4 kTr.
4 kTr. Okay, so this is going to be 4 kTr volt square per hertz. It's not sampled, it's continuous time. The input referred noise is this, at least for a single resistor. And in a delta sigma, we are not interested in the entire bandwidth, we are interested in, let us say, a small bandwidth of B. Because beyond this, my digital filter will filter it out. Okay, because after this, we have a digital filter, blah blah blah, same thing. So within this bandwidth, what will be the noise?
4 kTr.
4 kTr whole square per hertz. So the bandwidth is B. So this is going to be my noise, and based on this is how I will choose my resistor R. Again, this will be an assignment problem. There you will have a comprehensive comparison of these so that you will understand. But loosely speaking, also it should make sense, right? The on resistance ideally should be close to 0. So this will be huge compared to this. So now can you comment on the buffer? Which will be easier? In a discrete time it will be simpler, or continuous time it will be simpler? In a continuous time case, the buffer design is going to be much simpler, and sometimes you might not even need the buffer here because it's a simple resistor that you have to drive. It becomes easy. So that is one main thing. So the buffer design becomes now simpler, or you might not need. Okay. So that's the main difference between having a switch capacitor stage like this versus a continuous time stage like this. That is one motivation to push the sampler later. Okay. Cool.
Even looks simplistic.
Simplistic, yeah. And also, I mean, of course, the issue here is, again, nothing comes for free, right? I mean, I already mentioned when we discussed switch capacitor circuits. In switch capacitor circuits, the transfer function was dependent on ratios of capacitors, and this is accurately well controlled. Whereas here it depends on 1 by RC. That will be, there will be a lot of variation, so you have to do some kind of correction for it. Okay? Yeah, but anyways, let's look at the advantages alone. The second thing that is of benefit to us is this. Again, we only looked at two issues here. One is buffer, one is anti-aliasing. Looks like this problem is solved. Let's see if at all we get any benefit here. So actually for that, let me copy this. So now I am interested to find if there will be any kind of aliasing, right? Or if there will be what kind of aliasing will be present here. And since I am interested only in the signal properties, I will not consider the quantization noise. So I will only consider the signal here. So what I will do is this. First, I will push this L of S outside this summing block, right? So basically this reduces to this. I will push the L of S outside here like this. And then I will only have the sampler like this. Fine. So now the sampler is alone in the loop. I will also push it outside. So basically I'll have the sampler here and here, right? Fine. So this is the, I mean, same thing I've redrawn differently. And remember, now I'm interested in the signal transfer function. I want to find what happens if I apply a signal here and what do I get here. So the transfer function from this point to this point. So essentially that is a cascade of this guy, and
It has to be same only, right?
no, it's not that simpler, right? Because now we are sampler here, right?
Yeah.
That's what makes it tricky. So let's see. I mean, at least that's why I kind of took off the continuous time portion of the beginning itself, right? Because here it is sort of hybrid. To simplify things, I sort of push the continuous time filter separately outside. So I end up with only this portion, and let's see what is this portion. And for that, I'll copy paste the thing I had here. Okay. So remember that this is the transfer function from this point to this point is the noise transfer function, right? And here you see the input is applied, directly goes to the output, and an inverted version of this is filtered and sampled. So here you see the input is applied, goes to the output. Now you filter it, sample it, and invert it. So do you see anything similar between these two? I mean, here the input is applied here, it's basically inverted, filtered, and sampled. Input is applied here. I mean, the inversion happens later, but the same thing happens, right? It's filtered, sampled.
Yeah.
So can you comment on this transfer function now? No, here, I mean, is it okay? It's same as NTF, right? See, the transfer function from here to here is same as the transfer function from here to here. So it is the same thing. So the signal is added, and then it is fed back like this. You have filter, sampler, and inversion. Same thing happens. Signal is added, it is fed back. Here the inversion happens first, but that's a simple sign change, right? So this transfer function is same as my NTF of Z. Okay. So to find the overall signal transfer function, I just have to multiply these two fellows. So if I first plot the loop filter, this is continuous time frequency F. I know the loop filter is going to be cascade of continuous time integrators. So if I sketch it roughly, how do you think it will look like? It's a cascade of integrators. So at low frequencies, how do you think the gain will be? It will be very high. At DC it's infinite almost. I mean exactly infinite. So it will do something like this. Or maybe I'll color code it properly. So let us say this is this. Now we know how the NTF is going to look like. In discrete time, if I plot it from 0 to pi, the NTF looks like this. High pass NTF, right? And I mean, let's say I extend this, right? How do you think it will look like? I mean, that is, instead of just plotting from 0 to pi, how do you think it will behave from pi to 2 pi? It will be symmetric. It's a discrete time transfer function. You have periodicity in 2 pi. So this sort of does, because whatever happens at 0 happens at 2 pi, and this will keep repeating like this. Okay, and remember that this fellow is 0, this is pi is fs by 2. So here if I sketch it, it will look like this. Right, so this is 0 fs. Now I just have to take the product of these two graphs. So let me do it separately.
Yellow graph is what?
Hold on.
Yellow graph is what?
Yellow graph is the L of S, right? This guy is cascade of integrators. That's why it has this high gain at low frequencies and it tapers off at high frequencies. Let me push it here. Is that fine? The yellow one is the loop filter here, and the blue one is the noise transfer function that you have plotted. And the overall transfer function I am interested in is the cascade of these two guys, L of S and NTF. So if I take the product of these two, how do you think it will look like? This is the signal transfer function. At DC, we have something at infinite, something at 0. If I take the product, what will happen?
0.
One is infinite, one is 0.
No, one is exactly 0 and another is turning to infinite.
No. Infinitely large quantity versus infinitely, versus 0.
If it's exceptional or intentional?
There is nothing at exactly infinite, right? Everything tends to infinite. something will be exactly 0 and something can only tend to infinite.
Yeah.
So if I take a product of infinitely large quantity and 0, what happens? Finite, right? I mean, see, this is same as this, right? You have, let us say, 1 by x times x. No, see, a number can never become infinite, right? Infinity, it's always asymptotically goes to infinite, isn't it? See, this is basically this, isn't it?
You said x equals to tending to that is what.
I mean, see, strictly speaking,
I understand.
right?
This is finite, I understand.
I mean, does it make sense that the STF is finite?
Yeah.
You want the STF to be what at low frequencies? I mean, finite, but what value you want it to be? At low frequencies, you want the signal transfer function to be 1, and this also will become 1, right? So for, let us say, low frequencies, it sort of does this, and high frequencies it tapers off. So it does something like this. And what happens at Fs? It exactly falls to 0. And what happens at 2Fs? And then it will do this. Right? So it will have notches at multiples of Fs. Right? So remember, my signal bandwidth of interest is, let us say, till this point, low frequencies. Right? So now if, let us say, I look at some frequency, let us say delta f within this bandwidth from 0 to b. What is the frequency that can alias back to this? I have a frequency delta f. When I sample at Fs, what is the first frequency that can alias back to delta f? Huh? Yeah, okay. If it's that I'm looking at frequency delta f, so what is that frequency then? Fs minus delta f and Fs plus delta f, they can alias back to delta f. So this band of frequencies. So next is this guy, isn't it? Yeah. Around every multiple of Fs, those range of frequencies will fold back to DC. So this is the range of frequencies that can potentially alias back, and you see that they are basically almost 0, right? So looks like you don't need to have an anti-alias filter at all, because this guy itself is sort of rejecting potential frequencies which can alias back. Right? That's simply because, loosely speaking, in our circuit here, see, usually we sample it and then we do it, and only to prevent aliasing we should have a filter before, and looks like that is already done here, right? Before sampling we do have some kind of continuous time filter, right? That's why it sort of helps us. So this is usually called the implicit anti-aliasing property. Of continuous time delta sigma modulators. Okay. So in most applications, if you use this continuous time modulator, you might not even need to have an additional anti-alias filter, because the ADC itself is sort of providing you that anti-aliasing. So basically, this also solves your second problem of anti-alias filter. Right? I mean, you can also understand it if you look at the circuit implementation, right? So actually, maybe I can do that. Let's say you take this circuit. This might be better. Right. So again, I'm looking at signal property. I'll not consider quantizer and all. And remember, I have just taken one integrator, but you can have a higher order filter here. Let's say some h hat of s and then doing this. Cool. So okay. So let us say now I am interested to find if I apply a sinusoid at a frequency, let us say Fs. At the output, I am interested to see if this will alias. I mean, to what frequency this can alias back? To 0, which is DC, right? So I will see if there is anything that can alias back to DC. So I'll assume that output has a DC, because finally output is sampled. I can have only from 0 to Fs by 2. So let me see if I apply a tone at Fs, do I get anything at DC? Right? Because according to our thing, if I apply a tone at Fs, what happens? you can look at this plot. If I apply a tone at Fs, what will be the thing that will alias back? I mean, huh?
That one is the point.
Yeah, but here what is the signal transfer function at Fs? 0. I mean, exactly 0, right?
Is it? Okay.
You take the product also, it's 0, right? I mean, here I have hidden, but yeah. So if I apply a tone at Fs, what do you think will happen?
We will know.
Nothing will come at the output. There will be no aliasing happening from Fs to 0, right? And around Fs it's going to be small, but at multiples of Fs it's exactly 0. Clear? So let's quickly verify if that is the case, right? So I have applied a tone at Fs, and I am assuming that, let us say, there is aliasing, and let's see what happens, right? So what can you say about the current through this path? What will be the current?
That by R.
So this maybe right here, I don't want to write there. So this current is cos 2 pi Fst by R. What do you think will be the, say, current here? Output has only DC, so it's constant current DC, which is V0 by R. So what will be the capacitor current here? Let us say IC of t. Sum of these two. So let us say IC of t will be sum of these two. Okay. So in a negative feedback or in a working circuit, in steady state, can you comment anything about the current flowing through a capacitor? Current must be 0 or something else must be 0? I mean, why do you say the current must be 0?
DC current should be 0.
DC current is 0. Is that okay? See, remember, because the voltage is 1 by C integral I dt. If the current has any DC component, it means voltage kinds of ramps up and blows up. So stable negative feedback systems, it doesn't happen. Again, same thing. DC at the input of integrator is 0. This is an integrator for current to voltage. So average of this guy is 0. Right? So what is the average of this fellow? That's already 0. So which means 0 plus what is the average of this guy? It's the same, V0 by R, 0. So V0 is obviously 0. Okay. The same thing again and again, I mean in a different way. So that is the nice thing about this continuous time implementations, which is two things. One, now since the input impedance is purely resistive, the previous stage can easily drive this, unlike a switch capacitor stage. Second thing is, because you are pushing the sampler after a filter, this filter itself will provide you some inherent anti-aliasing, right? And loosely speaking, you know that any error that you add here, remember this is the same place where quantization also is also added. So any error added here at the output, it will be shaped by the noise transfer function. So any error added at small frequencies, it's almost negligible. So which means any kind of aliasing happening due to this sampling operation will also be, filtered by the same noise transfer function. That's what happened, right? This noise transfer function is what was making the alias terms go to 0. Right?
Then what is the H of S and forward?
I mean, you have to, from L of Z, you have to find an L of S, right? This is that L of S. This is that L of S totally. I mean, and I know for a fact that this will be a cascade of integrators. This integrator and higher order case, you will have rest of the filter. Okay. I mean, if I just have this guy, it's a first order system. For let us say third order modulator, I'll have a third order loop filter, I'll have cascade of 3 integrators.
And even that will be feed forward.
Yeah, I'm not drawing those, because for this, as long as you have one integrator here, this works. I mean, in fact, you can do a combination. Actually, people also do this, where you have the first one as continuous time filter, and then you can have the rest of it as discrete time filters. Let us say you want a third order. You see that the advantage you are getting is because the input stage is a continuous time integrator, and the input stage has to be a continuous time integrator for this guy to be resistor and this current to be 0, right? So you can have only one integrator in continuous time, and the other integrators can be in discrete time. You can do hybrid also. So yeah, so now what I want to highlight is this. So in the last class we saw, right, these are the three verticals we have, and any ADC is sort of a combination of these, right? Basically the algorithms we have are only flash and SAR. On top of it we have techniques. For increasing the speed we have time interleaving, and for increasing resolution we have pipelining and noise shaping, right? So until about, I'll say 30 years back, these were the three verticals people had to play with, and the moment people realized we can do this continuous time ADC, that opened an entirely new vertical. I mean, at least that's how I try to look at it. So now we can basically do it in a discrete time way. And I mean, in the late 90s to 2000s, this was the most popular thing: continuous time noise shaping ADCs with flash SAR. This gave rise to the continuous time delta sigma modulators, and they are highly popular, and you will find them in a whole bunch of places in your phones. So at let's say at high speeds, this continuous time ADCs are good, but at very low speeds where really high precision is important, we use switch capacitor circuits, because you want the transfer function to be exact. So in those cases you try to use switch capacitor circuits, but at relatively high speeds, this is much better. And other interesting thing is, again, now we can play around with anything, right? You can have multiple combinations in this. And the recent combination that is very popular, at least since the last 5 years, is this continuous time pipelining with flash SAR, anything. Okay. I mean, simply because, as I mentioned, at very high speeds where you need moderate resolutions, people use pipelining. And at high speeds, again, let us say talking at gigasamples per second, if you take a normal pipeline also, the regular stuff is this: input the switch capacitor states. Again, driving this is a problem. You'll have anti-aliasing filter issues.
In this, when we will have transfer functions, we don't have transfer functions.
Okay, if you see pipeline ADC, we had one ADC here, and then you had gain here, right? This can be G of S now. Okay, so the moment you do this solves again the same issues. And interestingly, this is this only 5 years old, and this is being done by analog devices. So very likely that in the next coming years you might find them in smartphones.